Hey everybody, I've been wanting to make a video about using NMR simulation, kind of like, for the lab and lab classes, organic uh, 2 lab at SF State, this chem336 class. It's also helpful in the organic 2 lecture course, chem335 is kind of an educational tool. NMR simulation is kind of the idea of using a computer to simulate an NMR spectrum. And that's helpful. I mean, not just to learn NMR, but also if you're in the laboratory and you synthesize a molecule, either you know what you made or you don't know what you made, you can try to figure out the structure, and how the structure maps to the spectrum using something called NMR simulation. So anyway, it's a pretty cool thing to demonstrate. So I'm going to do that in a little video here, and so let's get straight into it. This is kind of an example of how you something you might have to do in the organic lab. This is the aspirin synthesis and an example of the NMR spectrum and how we know the chemical structure, and we label the signals A, B, C, D, E, F. But then you have these signals down here that are part of it's the NMR spectrum for aspirin, and like trying to figure out which peaks correspond to which letters. Let's see, and I'll show a zoom in a second just to discuss the basic spectrum in a second. One thing that happened though is the F peak is this carboxylic acid up here. You have your little charts of chemical shifts, and the F peak is actually usually around the 11 or 12 region. We're not seeing it. And that's often in the real world, the carboxylic acids kind of get lost or washed out. So F is not going to be found, but we do have A, B, C, D, and E. The one peak that you might be able to identify just from your basic chemical or NMR knowledge is E, which is this ester CH3 group. And if you look on your little chart of chemical shifts, you would see that is next to a pi bond. Of course, the acetyl bond is a pi bond, and that usually comes in the 2 to 3 range. Well, there it is, 2 to 3. So without even anything, we can assign E to this signal. The ordering of A, B, C, and D is probably in this aromatic region, around 7 or 8. These 4 signals, and that's where the simulator is going to help us, and it shows the utility of the simulator. All right. Okay, now I'm going to, for the purpose of this exercise, I am going to show a zoom in of that region, and that's right here. And so you can see this is the aromatic region again. This is that peak we're calling E. And here's kind of like a zoom in of the aromatic region. We see what looks kind of like a doublet, a triplet, and a doublet. Based on the chemical structure, you should kind of know that, this is an ortho disubstituted benzenes. It means it's ortho. Ortho means these things are next door. And then we should expect 2 doublets and 2 triplets, right? This has how many neighbors? It has 1 neighbors right there. And it should, 1 plus 1 is 2. This should be a doublet. On the molecule, this should be a doublet. And this should be a doublet, right? Doublet. And these should be triplets, right? Triplet and triplet. Now, that said, the actual mapping, we do see 2 doublets and 2 triplets, right? A doublet, a triplet, and a triplet. That's cool. But the actual arrangement kind of depends on the chemical structure of this and the electronics and various things. And these are aspects that are a little hard to predict. I mean, some NMR experts could maybe figure out, where A, B, C, and D line up here. We do see, but the big thing is, we see 2 doublets, we see 2 triplets, but the computer simulator, or the NMR simulator, will specifically show us which is which. Okay, and that's really cool. What else? There's a little bit of we call it fine splitting. We see like these little mini doublet, mini doublet, mini doublet, mini doublet. You know, all of them have this. That is probably some kind of, it's called long distance coupling, which we're not going to really worry about, or I'm not going to worry about in this video. But it's like kind of like A, you know, A can totally see B, but A can also see C, for example, and that will cause maybe the little doublets. Let's not dwell on that right now. Okay. All right. So how do we get to this NMR simulator? And let's try it out. So I'm going to open up Google. I'm going to type NMRDB, which is the website, NMRDB. I'm doing this on a computer, right? I'm doing it on a PC. Should be able to do it on a Mac also. But it's this free, amazing website. And we're going to go to the Predict Proton NMR thing up top. And it comes up, and there's going to be a little, well, there's aspirin. I'm going to draw it from scratch because I want to show you from scratch. And before I do aspirin, you know, aspirin's shown here already. I'm going to do a test molecule, and you know, you can try a test molecule too. Like I'm going to do, I don't know, maybe this molecule here. Just to kind of review the n+1 rule, you know, the neighbors plus one, a little bit on chemical shift integration. And so once you draw something, you hit the simulate spectrum button. Okay, so now it shows the structure here. It shows the structure here also with all the hydrogens drawn out. And then what's really cool is I can move my mouse over the signals and kind of see where they show up top here. Or I can move my mouse on the hydrogens and see where they come. So this is amazingly helpful. Also, I can zoom in on the bottom. So I'm just going to drag over this little region. You're like, okay, yeah, you know, now you see the fine detail a bit. And of course, which of the signals is the downfield one, which is on the left? Well, that's the CH2 with chlorine on it. It's 3.6. And that also matches the little table of NMR shifts that we use. So 3.6 right there. And that's also a triplet. Why is it a triplet? Because there's two neighbors next door, plus one becomes a triplet, right? What's this? This is a quartet over here, and it's probably the next door CH2. And why is it a quartet? Because there's two neighbors on the right, one neighbor on the left. So that's 3 plus 1 quartet. This is this is the little central CH here. Probably you know, how many neighbors are there? If you count them, I see 1, 2, 3, 4, 5, 6, 7, 8 neighbors. Add one, it's a no net. Hard to see the 9 peaks. A no net is 9 peaks. Maybe if you really look closely, 1, 2, 3, 4, 5, 6, 7. A little hard to see, but there's 9. And sometimes you can't actually count all the lines perfectly, but we know there's a lot of neighbors there. Okay, and then we got the 2 CH3s that are overlapping 6 hydrogens, and that's kind of in the upfield region. All right, let's try aspirin now, just as a test. Also, notice there's a little question mark here. That's almost like a bug on the website. But if you just you may have to zoom around it with the mouse wheel or whatever, however you do your computer, to get the question mark out of the way. So to draw aspirin, I'm going to hit the eraser button. I'm going to find the benzene button, which is right down here. Click the benzene. Right now, my old molecule is still shown, but that'll go away in a second. Now I'm going to draw the stuff on aspirin. You may have to look at the structure. I'm going to hit the line button. I'm going to click up and draw. I draw all of the atoms, and then I add like oxygens and stuff later. So that's going to be eventually the carboxylic acid. But I'm going to make it another line down and a line up. Now, you know, that's going to be the structure of the carboxylic acid with oxygens. Then I'm going to go down, drag off the bottom to the right. That'll be that acetate, the other ester. I'm going to go up, and I'm going to go maybe up a little like that. Just make sure they don't connect. And this is all the atoms in aspirin. Now I just hit the oxygen. Click there, click there, click there. Oh, did I do this right? Yeah, I did it right. Yeah, good. There's aspirin, right? Now to simulate it, I'm going to hit the simulate button. And it did the simulation. It looks like I'm zoomed in here on the right. So to get out, to unzoom, I think I double click. Okay, there we are. Now this, if you remember, this kind of matches what we saw in the experimental data. I'm going to maybe click back, and you can see, basically the 4 signals on the left. 1, 2, 3, 4. This 7.2 is chloroform. It's the solvent. You can kind of ignore that. All right. There's also here 7.2. Mainly the 4 aromatic CHs, and then we have the CH3 at 2.3. Okay, let's go back to the simulation now. We all, like I already said, this peak on the right is very obvious. It's the CH3 group, and we don't need much simulation to help us assign that. Maybe the complicated ones, and even ones as a reasonably knowledgeable NMR person, I have trouble assigning the ones on the left, the aromatic ones. So I'm going to zoom in, just drag my mouse over this region. This is the aromatic region, and now it looks like we have a doublet, a triplet, and a doublet. Let's see if that order matches our experimental. So I'll go back to the PDF, and it's doublet, triplet, doublet. So that's cool. That shows the simulator is doing that right. And also, our goal is to really assign the letters A, B, C, and D to these 4 signals. I'm not going to do that for you. You got to do it yourself. But what I will show you is, like, if I move my mouse over the left peak, that's the doublet. Well, I see that comes up to this top proton. Oh, that's one of those letters. You can do the work. And then the triplet is there. You know what? Look on your assignment, and you'll see which letter that is. So that's showing the CH is assigned. The CH is assigned. Then we got the other triplet, which there's a little bit of a bug here, which is showing both of these CHs as one little thing, and it maps it's a little bug in the software. But you can see one of them is the triplet, which is probably that because there's 2 neighbors, and the other is the doublet. Net effect, you can assign the four letters using the simulation, and we're using a little bit of common sense. I mean, if we know there's 2 doublets, we know there's 2 triplets. If this is one doublet, where's the other doublet? The bottom. See what I'm saying? Anyway, I'm going to stop now, but this is hopefully a useful tool for you to, if you're given a chemical structure and you're given an NMR spectrum, to be kind of make a correspondence between the hydrogens on the structure to the signals on the NMR spectrum, right? Okay, but one thing I will show also, this also works for carbon NMR, and I don't emphasize carbon that much, in my courses. We use it like crazy in research, but I will show the predict carbon button because it does show the carbon NMR, and so it works the same way. It's kind of cool. This is let's see if it did it. There's my aspirin. It should be coming up. There it is, and now you can actually see the full carbon NMR spectrum, which is nice because we can use this to learn carbon NMR. And also, if you ever have to assign a carbon NMR, you can do it this way also. And we move our mouse over I just move my mouse over the carbons and see that where they come in the simulation. So that, and let's just go into this, maybe the aromatic region. And the acid and the ester come in the same place. So maybe it's simulating the acid on the left, the ester on the right up here at 160-ish. And then these are all aromatic signals. There's 6 of them because there's 6 carbons, 1, 2, 3, 4, 5, 6. And you can kind of move the mouse over each of them and make a prediction where they are. So they're really helpful if you're doing carbon NMR. If you're not doing carbon NMR, this isn't very useful. But I can basically go over each of them and see every one of those 6 carbons predicted pretty accurately. I mean, this usually matches the experiment. Okay, I'm going to stop.